bag of chips is your breakfast?
I got picked up like 15 minutes too early. So.
Okay, so let's talk a little about what we're up to in Physics 30 then. So this is just really bonus time in a way. Like I said yesterday, I think we're gonna get about 7 days worth in. Here's my hope, and I mean this is if this doesn't happen, don't stress it, but I think it would be amazing if we could get one assignment and one lab done ahead of when we start the actual semester in February. If you don't get that far, don't stress it. It's not really the end of the world. We're still swimming with time, obviously, right? But I think that would be fantastic. And if not, then don't worry about it. So today, tomorrow, Thursday, we'll try to rip through all the notes for the units. Momentum has, I think we've covered this in the 3 sets of notes that are here. And then we'll just do work time next week, because I know you guys have diplomas to get ready for, and you guys will have math, I guess. Math, social as well, right? Social. Because you have social on Monday, I think it was, right? Monday the exam week? So, but if you're able to get like one assignment and one lab mostly done, yeah, it'll be great. And then when we start in February, I think what we'll do is we'll probably, when we start up, we won't do anything specific the first day, but then we'll probably write a quiz pretty much right away after that. And we'll do like quiz, couple work days, unit test. So I should have printed off a progress log, but if I remember correctly, just so you guys are aware of what we're going to do, there's going to be 1 quiz, 1 unit test, 2 assignments, 1 lab. So we'll have just 5 tasks. 2 assignments, which I think I already had posted, 1 lab, quiz, unit test. Okay, let's talk momentum. Momentum is very closely associated with force. A lot of people, they actually get the 2 ideas maybe sometimes backwards in their mind. When they think of force, they're actually meaning momentum. And when they're thinking momentum, they actually think of force. And I can actually show you algebraically with the formulas why they actually are more or less equivalent to each other. No, they are equivalent to each other. It's just a different way of kind of approaching, just a different way of kind of seeing the world. You know how I talked about how you can solve problems using kinematics equations, but you can also solve problems using energy? I think you had a similar overlap here with momentum. Momentum is going to involve very similar concepts, and it's like a third way of kind of solving a problem. So sometimes you have options. That's one of the reasons why on that formula sheet, they talk about all of the different main physics principles, and often you can solve the same scenario using energy, or with accelerated motion, or with conservation momentum. So, anyways, let me start here by reading off what I've got here. You guys probably know the idea of momentum, and with it being wintertime right now, if you've ever had your car kind of skid through an intersection, that's basically the concept, right? You have momentum, and it's hard to bring something to a stop, right? Which is really similar, like I said, to our dynamics concept of force and the idea of inertia. If something is in motion, it has a tendency to stay at that same motion, and sometimes it's difficult to bring it to a stop. More difficult if it's either traveling faster or if it's really heavy, right? And some of you have already probably looked ahead at the formula for momentum. Momentum is the byproduct of mass times velocity. So if you have a high mass or you have a high velocity, it just makes it harder to stop something. You guys ever seen one of these things before? It's called a Newton's cradle. This is one of those sort of things where like you do like a paperweight on like some executive's desk, and like the little thing goes tick tick tick, right? This is a good example of momentum conservation. As this one right here clicks this one, all of that momentum gets transferred through all of them, and then the far one goes up, right? And then it comes back down, and it transfers all of its momentum, boom, 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 and kicks this one up the other side, right? And ideally, this thing should run for a very long time, because really the only reason why it would stop is due to loss of energy. Right? There's going to be a minimal amount of energy loss due to friction, maybe a little bit due to sound, but for the most part, this thing should run. I mean, it won't run indefinitely, obviously. Second law of thermodynamics will dictate that you always have to lose some energy. Well, lose, right? It's not actually lost, right? But this is a good example of something that involves momentum, the way that this thing is going to have a collision. That's actually a big part of what we're going to talk about tomorrow, the idea of what happens when things ram into each other. And there's a lot of really cool things you can do in this section. I have a plan to blow up a paint can one day, which I think is going to be super awesome. the logistics of doing it safely are obviously something to consider, but what I want to do is I want to use slow motion video cameras, kind of like they do on Mythbusters, or at least whatever video camera I can get. Go outside to a field, pump a paint can filled with methane gas, or whatever they put into our natural gas lines here, and light it and have it. And then we can actually watch it go in all different directions and see where the momentum is actually conserved. So I think that'd be really cool. So we wouldn't do that until June though, because it needs to be warm outside. Anyways, here's your formula. Momentum is mass times velocity. It's very straightforward. I mean, when I talked yesterday about the expectations of kids who are either going to hit the 50% acceptable level on diplomas or the 80% plus standard of excellence level, if you want to pass and get at least a 50, as is, you better know how to use this formula just straight up. But I don't mean to be rude, but like that should be a given by now, right? The harder part is, can you use this in conjunction with other formulas? That's what makes it more challenging. The big note I need you guys to have here, momentum is vector. Okay, we care about directions. So unlike energy where direction is not relevant, this is very relevant. So don't forget to include forward, left, right, north, east, whatever. As I was thinking about these slides earlier today, I thought I actually want to change the order up, if that's okay. So can you guys hop ahead to the other formula that's sitting here first? And then I'll come back and re-talk about those picture slides. Sometimes what we do is we talk about what it takes to stop something's momentum. If you want to change something's momentum, I would say 9 times out of 10 that involves stopping something, right? Like if you have a car driving on icy roads, usually what we're looking to do is take it from the 30 kilometers an hour that you go through the intersection to until finally you get down to 0, right? Like usually you're going from something down to nothing. It doesn't have to be down to nothing, it can just should be a change. But that's usually our goal, is to try to figure out how to change the object's momentum. And so we have a word for that. We call that an impulse. The impulse is basically whatever changes its momentum. The impulse could be a car slamming into a wall. The wall is providing the impulse for the car to stop. But if I can now go back to the slides I kind of skipped here, let's talk about different ways for things to have momentums. Let's say that you are going to provide the impulse to stop these 2 different scenarios here. One is you're going to try to stop a bowling ball. I mean, a bowling ball doesn't necessarily go all that fast, right? I mean, in the grand scheme of things, it takes, what, 4 or 5 seconds to get down the lane? But if you got hit by a bowling ball, I'm sure you wouldn't be thrilled about it because it's particularly heavy, right? And so for you to provide the impulse to change the momentum in the bowling ball, so long as it's going at a reasonable speed, due to its high mass, that's going to require quite an impulse. Does that make sense? Conversely, it could also require a high impulse to stop Mariano Rivera throwing a fastball. The ball itself is not that heavy, right? But he's throwing it at a pretty high velocity, like near 100 miles an hour, right? And so at that particular speed, if you were to get hit by the baseball, it's going to leave quite the welt on you. You know what I'm saying here? So either one is going to require quite the impulse in order to stop, either due to the high mass or the high velocity. The worst one is the next slide here. If you have both, this is where like collisions can be devastating, right? Where if you got a train, which is absolutely massive, and it's traveling at reasonable speed, I mean, I don't know whether this photo is doctored or not, but you can imagine the scenario, right? Like a car on the railroad tracks is going to get absolutely crushed, right? So much so that I'm not even sure how much impulse was provided by the car, because remember, an impulse is what's going to change an object's momentum. I'm not sure this train actually would have changed momentum all that much. I bet you would have plowed right through. You know what I mean? So. One more thought before I go back to the slide that I kind of went through here. Slowing or stopping the objects with momentum is often very dangerous and difficult. Here's a really good practical example. I don't know whether you guys are familiar with these. I am. I grew up in BC in the mountains. When you are driving down icy mountain roads, often as you're going on the downhill climb, they have these things called runaway lanes. Anyone ever heard or seen these before? The mountains. Basically, the concept is if your brakes are gone or you have no ability to stop, it would be terrifying because you would just keep going down that hill on icy conditions or with no brakes. And I mean, until you know what I mean? Like you keep going faster and faster and faster, it would be horrible, right? So they have these lanes off to the right-hand side usually so that if you absolutely need to, hopefully you can pull into the runway lane and go back up the hill so that that can stop and slow your momentum. Otherwise, yeah, who knows what will happen. So, that's a really good practical example. Okay, back to the concept of impulse then. Impulse is the word we use to describe trying to change momentum, and there are actually two different ways of finding this. The first way you can find it is by finding mass times change in velocity. So if you can calculate its change in velocity, which often is just the velocity you're given, because usually you're going from a speed down to 0. Sometimes you're going from, like, say 20 down to 10, or from 50 down to 40. Another possibility, if you're hitting a baseball, for example, the baseball could be coming towards you at 10, and let's say you hit it, and it goes back the other way at 10, then what's its change in velocity? 20. Does that make sense? Because it's coming towards you at 10, let's call that positive 10, right? You hit it back the other way, you hit it back at 10 the other way, well, now it's gone from positive 10 to negative 10, the difference in that would be 20. So, long story short though, this is one way of calculating your change in momentum. Know its mass, which should be consistent, and find its change in velocity. But the other way of accomplishing it is using force times the change in time. And I want to talk a bit about how this formula works and relates to dynamics for a second here. So, the first thing I like to do is just talk about the units involved. The units for mass are in kilograms. The units for velocity will be in meters per second. So essentially your impulse, the units of any impulse or of any momentum are kilograms meters per second. But another way of accomplishing this is force times change in time. A force is a mass times an acceleration. So this is mass times acceleration for force. Change in time would involve more seconds. And hopefully you can kind of visualize the units will work out the same on either side of the equation, because you'll cancel it, you'll have the same thing either way. That makes sense so far? One more thought. I want to focus on force. I also talked about how force is really similarly related to momentum, and sometimes we use the words incorrectly, but really you might just be using the wrong terminology, but you have the same concept, like the big overarching picture. And the reason why is that we know that force is equal to mass times acceleration, right? Well, what if I were to do just a quick little bit of algebra and divide by a change in time on both sides here? You can visualize this. Divide out the time on both sides. Well, what you'd be left with is a mass times velocity over time. What's velocity over time equal to? Acceleration. Which essentially reproves the exact same thing. Force is equal to mass times acceleration. We're just kind of doing a little proof like this. We would say force is mass times acceleration. Force would be mass times your like change in velocity over your change in time. Throw your change in time up over here. And now you've got the formula for impulse. Either this is your impulse or this is your impulse. Both of them really are a way to calculate your change in momentum. Does that make sense? Okay. Let's talk about that misnomer then of force versus momentum. Okay. Momentum is not force, although they are so closely related. I want to talk about what causes you to, like, say, get hurt, right? Like, let's go back to the example of you getting hit by this baseball right here. It's not the momentum that hurts you when the baseball hits you. It is the force of the baseball that hits you that causes the problem. Let me say that one more time. It's not the momentum so much that's the problem. Okay? I mean, momentum is going to cause the force. They're related. But when you get pelted by either the fastball here or by the bowling ball here, it's not momentum that's the problem. It's the force of hitting you that is the problem. That's what causes the force is ultimately the issue. So we shouldn't use those words synonymously. What does happen, though, is the most important thing then when you're trying to calculate something like this is the time. This time is very important. Let's say that you're about to get hit by an object. I don't care whatever it is, right? Something's going to hit you. Its mass is really consistent. Mass is what it is, right? And the velocity is going to go from whatever its speed is down to 0. So that's also fairly consistent. But if you want to avoid something hurting you, if you want to try to find a way to drop the force of something hitting you, what you're going to have to do then is find a way to increase the length of time that it takes. Now, I'm not talking about the length of time it takes for the ball to reach you. I'm talking about the length of time the ball is actually hitting you. Does that make sense? If I were to apply, sorry you guys really can't see this over there. If I were to apply this much force right there over a long period of time, that's not really all that much, right? What makes that karate chop thing so powerfully devastating is that it's over such a short period of time that that same momentum applied ends up having such a short amount of time, it increases the force. Can you visualize this? If this is going to be consistent, let's say that the mass is not going to change, and that your changes in velocity are not going to change. Those are pretty consistent. If you want to increase or decrease force, let's say you want to decrease the amount of force, well then up the amount of time. Or if you want there to be more force, then make it occur over less time. And that's what causes something to, like, force is the thing that causes things to, like, say, break or causes the bruise on you with the baseball. Does that make sense? Okay, let's do some math. Do some examples here. I think some of you already kind of tried some of these, haven't you? Did you do these ones already? Yeah. So, help me out with the math then. You've got a car moving at 10 kilometers an hour. How much momentum does it have? So, in terms of units, or in terms of variables, I don't actually know the reason why, but momentum has been designated with the letter P, and it is a vector. So your momentum is your mass times your velocity. Since we're not really looking for impulse at this point here, we don't need to worry about the delta V. We're just looking about how much momentum it just has as it's rolling. We're not stopping it yet. So 1,000 kilograms times by, it's 10 kilometers an hour. What's it? 3,600 seconds in an hour. And 1,000 meters in a kilometer. You get like 3 point something. What did you get for your velocity? 2.7 repeating? That makes sense. So that makes sense how I kind of am just doing that over there, convert that to meters per second, so that's your kilometer, kilograms, I mean. There's your meters per second, so I can do this in my head, that's that number of momentum. With sig digs, we'll have to make it 2.8 times 10 to the 3 kilogram meters per second. And let's just go with forward because we have no better knowledge of which way it's traveling. It's probably forward. Oh, you're right, just the magnitude. Okay, so then just 2.8 times 10 to the 3. Good call. You guys okay with that first one? I'm kind of glossing through that one pretty quick. Okay, let's calculate an impulse then. So a box was sliding across the table. Now we didn't stop it. I would say 9 times out of 10 it's probably stopping, but it doesn't have to. So we're just going to change its velocity down. Let's figure out the impulse imparted on the box. Before I get to that, let's talk about the relationship between this unit and previous units. Why is the box slowing down? Probably friction. It doesn't have to be though. It could be because I put my hand in the way and started to slow it down. Right? But some sort of force, an unbalanced force, is going to cause this thing to change. Newton's first law would say that this object should keep sliding at 4.6 meters per second indefinitely, but some sort of unbalanced force caused that. Whether it's an applied force, whether it's friction, we don't necessarily care what it is, but hopefully you guys agree. There are still forces involved. So we could still approach this from a force perspective. But let's do the impulse instead here. So impulse is either F delta T or it's M delta V. Those are your two options. Either one will get you an impulse. I don't think we have the F delta T information, so let's move on to the M delta V information. So mass was 0.015 kilograms. Your velocity is 3 meters per second. Right, because from 4.6 down to 1.6, it's changed by 3. 0.045. That'll work. Kilogram meters per second. And I don't know necessarily what we should use for the direction. Indicates something, but the impulse is going like the opposite way the box is sliding. So maybe like backwards. Something like that'll work. The box was sliding forward. The impulse must have been trying to move it backwards. It didn't actually make the box move backwards. It's just slowing down its momentum. Sound good? These are the basic ones. Okay. Why does a bullet hurt you? Okay, I know that sounds like a really stupid question, but the bullet hurts you because it puts a lot of force on your body, so much force that it's able to penetrate through your body, right? Does a bullet have a lot of mass? Well, no, it doesn't have a lot of mass, but it sure has a lot of velocity, right? But more important than that, when the bullet is coming in contact with a person, the amount of time that it's in contact with you for is very low. Does that make sense? Because of how fast it's traveling, one, not only is the bullet have a high amount of momentum, but two, the amount of time that it's going to be in contact with you is really not all that much, right? If I were to throw a bullet at you, I don't think you'd be all that afraid, right? For two reasons. One, it wasn't going that fast in the first place, and two, it will not have enough force to puncture skin and bone and flesh, right? So really there's that idea kind of comes to you twice. Let's use now the full formula, and this is the other way that this kind of gets used. You use the impulse formula, and you have the mass, you have the velocity, and you have time. We can use that to calculate how much force something would have. So this is pretty straightforward, I would say. We don't know the force. We do know that time is 3 times 10 to the minus 2. We know mass is 0.00875. And we know the change in velocity. Sometimes we just need to make sure we use some common sense here. It exits the rifle at a speed of 225. So it probably started at rest and ended at 225. So the 225 is the velocity change, right? So this is how much force the gun gave to the bullet, I guess. So I'm not actually talking about, in this example, a bullet hitting something yet, but you guys feel pretty comfortable being able to do this? So the other option is have all 4 variables in one big formula and use that to solve for something like, say, force. I got 65.6. Go. SIGDIGs, we need actually 65.6. Alright, 65.6 units. Newtons. Force is a vector. We should throw a direction on this, I guess. The force acting on the bullet is probably propelling it forward, I guess. Probably the best option. Sound good? Awesome. Okay, let's talk a little more about the theory behind this then. So, I was giving an example of a bullet. Let's do something a little less lethal. Let's talk about an egg breaking. It's only lethal to the egg. Okay. Let's say that the egg is going to fall. Okay. Is the mass of the egg going to change as it falls? Probably not. So that's making a difference. That can happen sometimes, by the way, in a scenario where an object breaks into pieces. Let's say that as it collides, it breaks into pieces. One piece goes that way, one piece goes that way. Then we do need to account for how the mass is changing. But as the egg is falling, let's pretend that it's more or less still one egg, right? It's not like one half of the egg is over there and one half's over there. The change in velocity is also going to be the same, because really, if I drop the egg, the velocity, let's say it lands on the bale of hay, or let's say it lands on the concrete, its velocity change is still going from something down to nothing. You know what I'm saying? Right? However fast it ends up traveling right as it hits, let's say it's about to hit the ground at 10 meters per second, it's going to go from 10 to 0 in an instant. Does that make sense? So the change in velocity isn't going to change either. So in both of these scenarios, our momentum, my pen just died. In both of these scenarios, the momentum is going to be consistent. The mass isn't going to change. The change in velocity isn't going to change. Oh boy, there we go. But the difference between it landing on the bed of straw and landing on the concrete, it's all about force. The force is what causes the egg to crack, right? So here, when it lands on the bed of straw, how long does it take for this thing to come to rest? Well, it takes maybe a second. Does that make sense? For the egg to, not as it falls, but like right before it hits the ground, right? As it hits, it comes to like on a nice little cushion. Does that make sense? That will then increase the amount of time. Well, if you increase the amount of time, it'll decrease the amount of force. Whereas right here, for this one right here, the reason why the force is comparatively so high is that the amount of impact time, the amount of time that it's actually hitting the ground for and changing its velocity from 10 to 0 instantly, that's low, so it causes there to be a high force. This principle is then very, very important in things like football helmets, cars, anything where excessive force becomes a problem. So my next couple of slides are more just kind of talking about the practical implications of this. I just found a picture of a football helmet, right? These days, concussions are a really big thing in hockey, whatever, soccer even, rugby, football, right? And if you want to try to avoid that, let's say that there's a linebacker who's about to hit a running back, right? Their masses aren't going to change, and the velocity is going to go from this to 0 in an instant, right? And essentially, that's what you're doing, right? You've got a brick wall, you're going from 100 down to 0 in no time. Well, if you can change the amount of time with cushioning, if the time goes up, force goes down. Does that make sense? That'll have an inverse relationship. So, similarly with like cars. Cars are designed to have crumple zones, where like the front end of the car is actually supposed to basically just shrivel up and crack. Hopefully none of you have been in a major accident, but this is why like sometimes older cars are actually quite safe. My first car was a 1984 Buick Skylark, really old boat of a car, but it was one of the safest cars possible because like the front of the car was massive. Right? Now, the front of the car being massive, it's not about having me be far away from the distance. It's the idea that as the collision happens, there's more to compress. And the more to compress means it'll take longer. Yeah, we can get breakfast, Joss. Go please. Hello. Anybody hungry? It looks like they've got yogurt, muffins, and fruit.
There's cheese.
Where's Andy? Sorry.
You guys feel like you get the picture of what I'm talking about here with the car concept? One of the cars that drives me crazy is, you guys know the, what's it called? It's the 4.2 by the company that makes a really small car. What was that? What's the name of the car that's like the smart car? That's what it is, right? The 4.2 is the brand, right? The car is so small in the front that I feel like it's very unsafe due to the fact that there's going to be no crumple zone on it, right? And so if someone gets into a head-on collision, there's no way to decrease the amount of force. Because the impulse is what it's going to be, right? You're going to be going at 100 on the highway, your mass is what it is, and you're going to be going from 100 to 0 in a crash, right? That's not changing. But if we can increase the amount of time, we decrease the force, right? So you want to have as much distance as possible. Not just because you want to keep yourself away from the oncoming traffic from hitting you specifically, but it's that distance. The longer it takes for this through here to crumple, the more it saves your life. And we're going to do an example, I think, in a second here where you can see that it doesn't take a whole lot to help decrease the force drastically. So, yeah, here's another picture of crumple zones in the car. Ideally, your trunk, your front end, those are supposed to be things that will help decrease. Now, it's not going to decrease the momentum. Okay. Momentum is going to be what it is. You guys feel that concept here? But it can hopefully help decrease force. And force, that's what's going to help you survive a car crash. Okay, so let's do an example here. The first example here, we're going to have a guy basically, I mean, sorry that this is kind of morbid here, but this guy is going to be in a car accident. he's going 65 to 0 like nothing, right? In the first example, he's going to hit the wall and come to rest in no time flat. In the second example, there's going to be an airbag. And so the airbag is hopefully going to help bring him to rest in a little bit less time. Ideally, this airbag should then help prevent him from getting whiplash and concussions and stuff like that. You know what I'm saying here? So let's try the example. The formula is force times change in time is mass times change in velocity. We're looking for force. So your force is going to be his mass times by his velocity. 65 divided by 3.6. We need its meters per second number. I got 18.05 repeating. Any of you guys already done this calculation? Okay. So mass is 75, in meters per second, his velocity is 18.05. He's going from that to 0, right? Because he's going to come to a complete stop. And in the first example, the amount of time he gets is going to be basically nothing, right? There's no airbag to slow him down. He's going to go and whiplash, huge concussion, huge neck problems. In the exact same example here on the second one, I'm hardly going to change anything except for, in the second example, I mean, 0.34 seconds is still a blink of an eye, right? It's not like the crash is now slow motion, right? Like it's still pretty quick, right? But let's see the difference in how much force there's going to be on the person. So 75 times by 1805 divided by 0.050 gives us 27083 newtons of force on you. Do the exact same calculation, but put it in a third of a second. This thing now drops down to 3982 newtons. I mean, proportionally, that's huge in terms of how much less force, right? So you can see why things like crumple zones, airbags, these sorts of safety features are mandated. Let's just finish this up with proper sig digs. This would be 2.7 times 10 to the 4 newtons. This would be 4.0 times 10 to the 3 newtons. That makes sense? I feel like I've been really redundant today, but just to make sure we're clear, there's a huge relationship between momentum and force, dynamics, energy, and momentum. They all kind of relate together in a way. But make sure you use your terminology properly because I can totally see there being theory questions involving this. Your impulse is about momentum change. But the thing that's going to cause you hurt and pain and issues is really the force that's applied. They are very much related, but it's actually time. Time is the link that relates them, really. Your impulse is related to your force by time. Lessen the time, increase the force. Oh, wait, last thought. We can also do lots of graphs. And I pointed out on that document I gave you yesterday that they're going to give you graphs on the diploma. That's a pretty much an expectation here. Your job is going to be how to interpret them. I would say there's two main things you need to know how to do with any graph. For one, you need to know how to calculate a graph's slope. You guys feel comfortable calculating a graph's slope? Okay. They might give you a picture of a graph. They might give you data and ask you to draw a graph and then calculate the graph from that data and then calculate slope from there. We'll do lots of examples in this over time, but that's one thing, calculate a slope. The other thing they might ask you to do is calculate the area under a curve, and that's where we're going here. Okay. If you have a formula where there is like x divided by y, that's your slope. But if you have a formula where there's x times by y, that's where you have to find your area. And that's really what's happening here. If we want to calculate force times the change in time for your impulse, we need to find the area underneath the graph by using a basic shape. And the shape is probably going to be either a triangle or a square. Like those are your options, or rectangle, I guess, right? So if you were to calculate the area of this graph by saying, well, from here to here is 17, and from here to here is 30, if you multiply those numbers by each other, that would then, in theory, give you your impulse. So This is pretty straightforward. You just have to remember what to do. So for this one here, let's calculate the final velocity of the car. So first things first. Using the graph itself, it looks like as time goes on, the amount of force happens to be increasing, right? And we know that force times change in time is going to equal your impulse, which is equal to your mass times your change in velocity. Is our force consistent, however? No. As you look at this particular example, the force began with nothing. I feel like I'm in a Star Wars movie whenever I talk about the force so much. The amount of force you have starts at 0, right? There's no force to begin with, and the force is slowly but surely increasing over time. It makes it kind of hard to use this formula because we don't have a consistent number for force. I can't just throw in 3,012 newtons for force because that's not the actual amount of force it used the entire time. Does that make sense? But I can use a geometric shape. 1/2 of base height would be your area. So if you did 1/2 of 5.78 and multiply it by 3012, that would ultimately get you the same thing either way. So 5.78 times 3012 divided by 2. I've calculated an impulse of 8704.68. Now, if the question just purely asked for the impulse, we would stop there. But it asked for the final velocity of the car. So I got to keep going a little bit here. This area of the triangle, which got me this impulse right here, that's also equal to mass times velocity. I know it's mass though, right? Because mass is 1,500. So if I divide by 1,500, I should be able to get my change in velocity. I've calculated a change in velocity of 5.80. Right. And I think it would be fair to say here that because it started from rest, that's the last key here. This was a change in velocity, but since it started at rest, we now know that the final velocity would be 5.80 meters per second. Forward, I guess. That's more challenging, right? That's the question where it's not just calculate a slope, but we had to use a graph to calculate an impulse, use the impulse in another formula to get the remaining variable. But you're going to get stuff like that in pretty much all of our units going forward. So last one. Yeah, last one. I quite like this one here. This is a graph of the interaction between the force of a golf ball being hit by a golf club. And if you can kind of picture this, I don't know, whoever your golfer is, takes a swing at the golf ball, right? As the club begins to hit the ball, really there is no force, and it slowly builds up, right? And then, you guys ever see those photos where like the hockey stick or the driver starts to flex a little bit, right? And you can actually see that moment in time where like it's flexed, right? As the ball or puck now leaves, now the amount of force starts to decrease, because they're no longer really in contact with each other, right? Now the puck and the stick, or the ball and the club, are starting to separate slightly as that like elasticity of it kind of rebounds out. And so now the force will come back down again. So my question now is very similar. Let's calculate impulse and velocity of this one. I mean, it's almost the exact same sort of thing here. If you want to calculate the impulse, we need a force versus time graph. We have that. So we need the area. Only we have to read the graph a little differently here. It looks like this is going from point 1 up until 1.1. You guys agree with that? So I'd say the base is 1.0 units. The height, I think it's pretty straightforward. It looks like it's up to 5,000. So that should be 2,500 kilogram meters per second. Ooh, I missed something. Milliseconds? Yeah, good catch. I just looked at that right now. That's also in milliseconds. So milli is times 10 to the minus 3. So this should be 2.5 kilogram meters per second. Yeah, that makes sense, right? Because it should be times 10 to the minus 3. so times 10 to the minus 3 on all of this here. Does that work? Okay, so there's our area, that's our impulse. And that's going to be equal to force times change in time. But we don't want that part, we want the mass times change in velocity. So we just did this last time, right? We'll divide by the mass of 0.0459. Divide by 0.0459, which is its mass. And that should get us its velocity.
That's a roll, it's just W.
I've got a change in velocity of, I calculated 54.5, something like that. And that would then be in meters per second. That actually seems to be on the right scale of magnitude, right? Like the guy hitting a golf ball, 54 meters per second. I mean, as it leaves the club, we're talking the instant it leaves the club, right? I mean, over time it's slowing down due to frictional forces, but as that slow motion shot of the ball being compressed into the club. That makes sense? Okay. So that's day one. Tomorrow's kind of the main day on this stuff here. What we're going to talk about tomorrow, if you've looked at kind of the notes a little bit, tomorrow's kind of the fun day. Tomorrow we're going to talk about collisions and the different ways that things can smash into each other. And I mean, in a way, I quite enjoy this section here because it's, I don't know, it's got a big bang to it, obviously, right? We're talking about baseballs being hit. We're talking about tennis rackets, or, I mean, I've got lots of examples here of car crashes, pool balls. So, anyways, that's tomorrow's plan. You guys feel comfortable today, though? So, quick summary. I would say, what's the key stuff you need to know? You need to know how to calculate momentum on its own, but that's really basic, mass times velocity. You need to know how to calculate impulse, either mass times change in velocity or force times change in time. You should know how to put both of those formulas together and do the F delta T equals M delta V formula. You should know the theory behind force versus momentum and how they are very similar, but there is a difference between them. And you should know how to use some graphs. I'd say that's kind of the basics for today. Rebecca. Oh, good catch. Based on it being off of the graph, since the graph down there was giving 2 sig digs on the time, I should have really made this 54. Yeah, you should only have 2 sig digs based on the graph's information, right? Because this axis of the graph right here is giving us 3 sig digs, but this axis is giving us, well, the difference between it, I guess, would be from 1.1 down to 1.0. So I guess officially you'd take 1.1 minus 0.1. When you subtract them, it would be 1.0 based on like the precision there. Remember the rules for subtracting? Subtracting and adding rules are based on where your precision lines up with. So I would say based on this right here, this gives us 2 sig digs, this gives us 4 sig digs, and this gives us 3. So I'd say 2. On a question like that on a diploma, they would probably be very specific, and they would say round your answer to 3 sig digs, so make sure it's clear. All right. Yes, feel good? Okay, cool. No answer means yes. Okay, yeah, take the rest of the class to work on, I don't know, whatever. Since we have half an hour, so you can probably start on the assignment a little bit if you want.